All right, we're going to talk about the greatest integer function. The greatest integer function has probably one of the weirdest notations in math. And it's of the form, and it looks like, if I was to do it for you guys, you take a bracket, and then you put another double line on it. Again, you do a bracket, and you can actually just add a bracket to it if you so wish as well. This is called the greatest integer function. You do find these in the real world, especially at the post office when your package goes above a certain weight, and so you got to pay the next level up when it comes to shipping. So these are seen in the real world. This has a lot to do with shipping. It is a discontinuous function, and it will have breaks or gaps in it. So it's going to have a lot of them, all right? It just means that when you see this, that we're going to be rounding down. Sometimes in upper level classes, we call this a floor function. But it just means that we're going to round down our answers to the nearest integer. Let me explain that. All right, so let's talk about rounding down. I'm going to do positive integers first. So if we have something like, it says the greatest integer of, let's do 4.8. We are normally used to rounding up, but that is not what this is saying. All right, this is saying if you have the number 4.8, let's say it's here, when you round down, you're going to round downward to the nearest integer, to the nearest counting number if you want. And so the answer to this one will be 4. Again, this notation is telling me that I need to round down. If I have another number such as, let's do 3.01, well, this will feel comfortable for most of us because we're like, well, that's closer to 3. And that's true. But again, we always round down. So again, if there's like a 2.5, you round down to 2. If you've got a 0.5, you don't round up. I don't care if you have a 0.99, you always round down. So this is the pattern. It's always going in the downward direction. You're going, it's almost as if you're going to go towards negative infinity. So you just keep on rounding to the next counting number or the nearest what we call integer. That's how rounding down is for positives. It feels a little bit stranger when we're dealing with negatives. So if I have, let's do the proper notation here. If I have negative 0.8, and negative 0.8 is here, let's just say. Oops, let's finish that up, shall we? Again, you round down to the nearest integer. So when I round this, I'm going to round it to the nearest integer, which is negative 1. So your answer should always be a counting number, all right, or some type of whole number up here if you want, but normally it's an integer because we can have positive, negatives, and zeros. If I give you something like negative 1.1, as much as you want to round to the nearest number, you round down. So if negative 1.1 is here, you round down to the nearest integer. So this is going to give you negative 2. It feels weird, especially with the negatives, because we're not used to keep on rounding down. If I have negative 2.4, I round to negative 3. If I have 3.999, I round to negative 4. Let's do a few more examples, but without the graph. The whole numbers, you've got to love whole numbers, because when I put in, or in this case, 9 is a whole number, but let's just talk integers on this whole thing. When I have a counting number, and that's all I have 9, then guess what? My answer is going to be 9. I round down to the nearest integer. I am already at 9, my answer is 9. Same thing goes. Negative 17, it's not a decimal, it is a counting number. It is at negative 17, my answer is negative 17. 0, it's not a decimal, it's already at 0, my answer is 0. If we were to look at decimals, this is where it gets a little confusing for most students. Again, we want to round down. 2.7, yeah, it's close to 3, but no, 3 is not our main number that we want to go to. We round down. So if there's a difference between 2 and 3 when it comes to this greatest integer function. If 2.7 is here, you round down. My answer is 2. 1.92, again, we're used to rounding up because it's just easier for us, but a greatest integer function says, hey, you didn't meet the 2 pound limit, therefore you can pay the 1 pound limit when you ship. That's kind of the way it goes. So again, you're rounding down. 1.92, round down to the nearest integer. You don't round down to 0, you round down to 1. That's the reason why they call it the nearest integer. 0.5 is between 0 and 1, and again, you round down, so you got an answer of 0. We can take a look at a couple other examples again. If I give you the greatest integer function of negative 2.5, negative 2.5 is here on the number line. Again, when you do the greatest integer function, which is set off by the double brackets, you are going to round down to the nearest integer. So this will round down to negative 3. I want to emphasize the negatives because the negatives seem to be the hardest thing when I teach this for students. So I have negative 5.07. It's really, really close to negative 5. Again, what we're trying to do is round down. It didn't touch negative 5. It's close, but again, this is rounding down. So we round always to the left whenever we do this function. So our answer is negative 6. Looking at the greatest integer function for negative 11.8. Here is negative 11.8, let's just say. Again, you always go to the left of the number. No matter what it is, it's always to the left, just like Beyonce's song. And we get negative 12. If we were to do a new example, let's take a look at this one. This is always interesting when I give students this. What if I give you pi? Well, as we know, pi, and for short, let's just do that. Pi represents what? 3.14. It's been a while if you haven't had geometry. 3.14. Well, on the number line, as we know, here is 3, here's 4. 3.14, let's just pretend like it's right there. If this is 3.14, the greatest integer function says I'm going to round down. So my final answer is going to be 3. So don't let something like this scare you when they give you pi. But that's all there is to it as far as finding the greatest integer function. As far as graphing greatest integer functions, let's take a look at this, because I did tell you that it was a discontinuous function. And take a look at this. This is the original graph. This is the function, the greatest integer, x. And if you watch how I do this, this is really interesting. We have, notice that on one end, it is a closed circle. Got it. Okay, that's good. And then on the other end, it is an open circle. And in between, you just connect these. Then you go to the next level up. And notice how each closed will fill in this open circle. Yeah, for every level. So there is a jump as far as the y values. I'm at 0. Then there's a space on the y from here to here. So this is now at 1. Then there's a space from here to here, from here to here, from 1 to 2. And this is the reason why this is a discontinuous function, because I got to lift up my pencil to get to the next level. Again, it's called a step function, because if you were to actually walk up these, you would actually say, duh, you know, it's just like a step. Let's talk about the domain, though, on this function. All right, we want to talk about the domain. The domain is going to be the set of reals, but I'm going to show you why. And also remember that a closed circle overrides an open circle. In other words, a closed circle, if it fills in the open circle, it is now closed. So this will turn into a closed circle when they overlap. So as it stands, my function looks like this. I've got closed, then open. It goes up a unit, closed, then open, then goes up, closed, then open, and so on. If you were to take these and all of a sudden collapse them onto one line, you would see that you would get closed, 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 closed. And so this is the reason why our domain is a set of all real numbers. Take them and just collapse all of your lines, all of your segments into one, and you will see that they form a straight line of which all the open circles are filled in. If we want to talk about the range, again, the same goes. The closed circle overrides an open circle. It fills it in. It is a closed circle. So let's take a look at the range. If I were to line them up on the y-axis, this is kind of what it would look like. So what I did was I just pushed them all to the y-axis. I know they're not, but basically if I want to figure out the range on my own, this is how I'm going to do it. So I'm kind of making a ladder going up this way, even though this is not the graph. Again, I'm just trying to find range and make sense of it. So if you notice, if I pushed them all to the y-axis, I would have this. And you can see I'm here at -1, then I'm here at 0, then I'm here at 1, and then I'm here at 2. I have nothing between -1 and 0 on the y-axis. I have another jump between 0 and 1. I have another jump between 1 and 2. Now, as we know, if I have a closed circle and an open circle on the same level, it is going to fill it in. So what I'm going to end up having is basically, think of them as solid dots along your counting numbers or along your integers at -1, at 0, at 1, and at 2, and so on. And so when we want to write the range, this is the one that gets the most funkiest when it comes to range. Because I can't say whole numbers because whole numbers deals with 0 on up. And when we talk about a number line, especially in the y-axis, we're talking about negative numbers as well. And so we call them the set of integers. And the set of integers is better known as this double stroke z. So you got a z going on, and then you just kind of tack on another z on top of it, if you so wish. So this is called the set of integers. In other words, it is from -infinity to +infinity, but I don't have fractions or anything like that. What I have is strictly -4, -3, -2, -1, 0, 1, 2, 3, 4, and that's called the set of integers. This would be your answer, or they may even say this in your book, the set of integers. But this is the shortcut notation, the college notation for the set of integers. So no, you cannot say all real numbers. All real numbers imply fractions and all the stuff in between -1 and 0. So we can only say, I can't say counting numbers because again, this is college notation. We call that the set of integers. That would be your notation. Or you can say that as well, the set of integers. But we're here to learn college, so let's call it what it is, this fancy notation right here.